All right, you guys ready? I see several notebooks open, several not.
Mine's open. Good Nick.
This should mostly be already in your brain. Okay, this should be mostly reviewed. Shh. Shush. All right, up on the screen. Change of state. 9.5. What is that a picture of?
It's a tractor.
It's a
Steam
tractor.
train.
A steam train?
Steam
tractor.
It's a tractor that looks like a train.
A steam tractor.
A choo-choo train.
Steam tractor.
More like a choo-choo
So,
tractor.
here we go. Yeah. A choo-choo tractor. Very good. All right. Where's your notebook?
Oh, yeah.
Before the internal combustion engine was invented. Calm down. Before the internal combustion engine was invented, steam engines were the power source for ships, locomotives, tractors, lumber saws, and most industrial machines. Coal or wood was burned to boil water into steam, which ran the engine. So you're combusting the coal or wood, but it's not an internal combustion engine because the combustion is not happening where? In the cylinders, right? You're injecting the steam into the cylinders under pressure to drive the pistons. Make sense? Change of state. Most substances may exist in any of the three common states of matter. In the gaseous, three. How many states of matter are there?
3.
Four.
Plasma.
Now, I want you to put this in your notes this way. So solid, put it at the bottom. If you want to flip it, that's fine, but then you got to flip everything else too, right? So if we go from solid, this is the least excited state of matter, yes?
Yep.
Lowest temperature,
Yep.
okay? Get more energy into the mix, so to speak, and we go to a liquid, to a gas, and then finally to a plasma. Plasma is the most excited state of matter. Solid is the least
Isn't that
excited.
what the sun is?
The sun, yeah, parts of the sun are plasma. All right,
Plasma was like blood.
it's a different type of plasma. So yeah,
Plasma's like the sun is electricity, right? Or no, lightning. They're calling you again.
great. Could we teach the lesson? Okay, so plasma, blood plasma is the liquid portion of your blood. Okay. Lightning, yes. Somebody said lightning. Yeah, when lightning goes through the column of air it's going through, it blows it apart, literally. If there was rain falling or whatever, right, that would get blown apart too, but mostly gas going through the air, right? So that lightning bolt would take the molecules of air and shatter them, essentially, turning them into plasma. Yes?
You said liquid part of blood, but isn't blood liquid?
If you took the plasma out, it wouldn't be. So remember we talked about centrifugal forces? Centrifugal forces? So if you have a centrifuge with like a vial of blood or several vials of blood and spin them real fast, the blood would separate out. So you can actually remove the red blood cells and put the plasma back in. Does that make sense? Okay. Blood plasma is actually like a yellowish color.
Like pee?
Yeah, kind of like pee.
Like clear?
Well, depends on how hydrated you are, I guess, right? So, yeah, the red color of your blood comes from the
Oxygen.
hemoglobin.
Hemoglobin.
Okay.
Mainly it's
What?
Bro.
All right. In the gaseous state. Hello?
Yep.
Not making a very good video for your peers.
Sorry.
Thank you. In the gaseous state, molecular motion has completely overcome any attraction between the particles. Stop holding hands.
Aw.
And the particles are totally separate from each other. There are large spaces between the particles and they move large distances between collisions. In the liquid state, the molecular motion and molecular attractions are more balanced. While the particles stay more or less in contact with each other, they're free to move and can slide past one another easily. That's a liquid. In the solid state, the attractive forces are dominant. The particles are pulled together in a tightly packed pattern, which does not allow particles to pass easily past one another. The molecular motion in this form is essentially reduced to a vibration in place. Increasing the temperature of a substance means increasing the molecular motion or kinetic energy of the molecules in the substance. In the phase in which the substance exists is the result of the competition between attractive forces and molecular motion. So attractive forces win. Attractive forces are starting to get balanced with the molecular force. And then molecular force motion is winning, and then it completely takes over. So the molecules themselves fly apart. Does that make sense? Plasma, the molecules have flown apart. They've torn themselves apart. There's too much energy. Questions on that? Okay. All right, so in these beakers, not beakers, what are these called? Science people?
Glass.
Breakers.
Not breakers,
Beaker.
flasks. Okay, whatever the heck they are. In these triangular glasses, they're corked too. The solid, the one that has solid in it, if you were to break it, the solids would just sit there in their current state, right? Unless it's like a powder, but then it'd still be a solid.
Where would the gas go?
Hold on, I'm getting there. I'm getting there. The liquid, if you broke that, the liquid would spill out. Yes.
Yeah.
Indeed.
Flow out, you might say. With the gas, if you broke it, the gas would escape in every direction. Yes?
Yeah.
Unless it was heavier than air, then it would spill out and flow more like a liquid.
Yeah.
Flow. Liquid, gas. What's a fluid then?
Oh, liquid.
A fluid is a liquid?
Yeah.
Yeah.
No.
Does a fluid have to be a liquid?
No.
It could be a gas.
Something that moves like
Guys, an easy definition to kind of try to remember it is fluids flow. Can a gas flow?
Yeah.
Can a liquid flow?
Yeah.
They're both fluids. All right. So we understand that as we add energy, see how it says add energy that way? To go from a solid to a liquid, we have to add energy. Liquid to gas, got to add energy. Gas to a plasma, got to add energy. If we want to go this way, we have to remove energy. Does that make sense? All right, cool. Moving on. We've got different names for things, though. Some of them might not be super familiar to you. We certainly don't use them in our day-to-day language. Heat of fusion. If you don't know what that means, I've got it pulled up here, highlighted. Heat of fusion is the potential energy absorbed by a solid as it changes to a liquid. Heat of fusion is energy absorbed by a solid as it changes to a liquid. Which in common language we would say it's doing what?
Melting.
It's melting. Good. The heat of fusion is what causes it to melt. Boiling point. You understand what boiling point is?
Yeah, when
It's the temperature at which
It
you go
boils.
from a
boils. From my solid
Liquid to a gas.
Solid to
No.
Liquid to gas.
liquid to a gas.
liquid to a
Yeah,
gas.
liquid to a gas.
Oh, boiling.
Don't you feel silly?
Yeah.
All right.
Melting.
The amount of potential energy necessary for a phase change to gaseous form is called the heat of vaporization. Heat of vaporization. So to make it boil, you have potential energy necessary, liquid to gas, to boil. Heat of vaporization. I like this chart. It's showing you, hey, as you are adding heat, as heat energy is added, temperature goes up. Temperature stays at the freezing point until all of it is melted. Does that make sense? So this is dealing with water ice. So you can increase that temperature of the chunk of ice up to 0 Celsius, right? For a freezing point of water. It's going to stay there until all of the ice has melted. Like if you've got ice in a glass. We're going to show it here in a second. And then once it's all liquid, then it'll start increasing in temperature again until it gets to the boiling point. And then it's going to stay at the boiling point until all of that water has evaporated. Does that make sense? And then what will start increasing in temperature then?
Whatever.
The gas, the water
Vape.
vapor. Good. So I'm going to skip down to this so you can see. You can certainly play with this later if you want on your own. I'm just going to do a quick version of it. So we're going to go from solid to liquid. Notice the ice is at negative 50 Celsius. It's cold. So you start adding heat. We get up to the melting point, so it starts to melt. But notice the temperature's stuck at 0 Celsius until all of the ice has melted. Then it'll start to increase again. Starting to ramp up as you add heat. Now, if we went to liquid to gas and hit play, so we got 50-degree water, start adding heat, gets warmer, gets warmer, gets warmer until it hits the boiling point, and then it's going to stay at the boiling point even as you're adding heat. It won't increase the temperature until all of the water has boiled off. Starting to boil. Yeah, it's going away. Boiling off. Still at 100 degrees Celsius until all of it's gone, and then you would see an increase in the water vapor temperature. And we can do the same thing going backward. All right. Cool. A bunch of heats of fusion. We got a chart showing out if we want to do that. We will not be doing that in this class. Specific heat, though, definition is the amount of heat necessary to raise one mass unit of that particular substance by one temperature unit. We got the formulas, which we are not going to use. This is an intro, not a full-on. This one's not bad. I'm going to skip it anyway. Okay. If it's not in your forehead, it's in your nose. Most substances may exist in any of 3 common states of matter: solid, liquid, or gas. The phase in which a substance exists, these are the different phases, right, is the result of a competition between attractive forces and molecular motion. The potential energy absorbed by a solid as it changes to a liquid is called the heat of fusion or the heat of melting. The amount of potential energy necessary for a phase-changed gaseous form is called the heat of vaporization. And then we have our formulas. All right, now we're going to switch to AI-generated questions and things. It did add for us, thank goodness, it did add for us common changes state to include melting, solid to liquid, freezing, liquid to solid, evaporation or vaporization, liquid to gas. Condensation is gas to liquid. Sublimation, is that term new for anybody?
Yes.
Sublimation, if it's new to you,
It's not new, but I remember.
okay, so you might want to throw it in your notes, okay? Sublimation is going straight from a solid to a gas. You skip over the liquid phase. I'll explain it here in a moment. And then the reverse of that is deposition, going straight from a gas to a solid. Again, skipping over the liquid phase. Energy is either absorbed or released during these changes. For example, melting requires energy to break the bonds in a solid, while freezing releases energy as a liquid forms a solid. Temperature and pressure affect how and when these changes occur. Okay, so keep this in mind as we go through these, all right? Change from a solid to liquid is called melting. The word bank's right here, by the way. Condensation, sublimation, boiling, melting, and exothermic. So change from a solid to a liquid is called melting. When a gas becomes a liquid, the process is called
Condensation.
very good, condensation. Number 3, blank is a change directly from a solid to a gas. Sublimation. Good. Freezing is an example of an energy exothermic process because heat is released. If heat were absorbed, it would be called endothermic, if you want to put that in your notes. You guys are going to see that a lot when you take chemistry. A lot of this is like more chemistry, or at least as much chemistry as it is physics. The temperature at which a liquid becomes a gas at a given pressure is called the Liquid to gas.
Boiling.
Boiling point. Good. All right, here we go. As we answer these, we'll answer the question you had, okay? Like, how does that work? Which change of state requires the input of energy to occur? Adding energy. So you'd be going up this list. Which of them does it go up the list? Freezing? No, freezing would be going from liquid to solid, right? How about condensation? No, that's going down the list. How about melting?
Yes.
Yes. Deposition? Deposition would be going from a gas to a solid. It would be going down. So no. Questions on that one? Okay. At standard atmospheric pressure, water boils at 100 degrees Celsius. Yes?
Yeah.
Which statement best describes boiling? Boiling is the same as condensation. No, it's not the same thing. Boiling is vaporization that occurs throughout the liquid. Do we kind of like that answer?
Yeah.
Do we want to keep looking at the rest of them?
Yes.
Yes, always. Boiling only happens at the surface of a liquid. No, haven't you ever seen, like, in a pot, you see the bubbles forming even at the bottom, right? And then finally, deboiling releases energy to the surroundings. No, you're having to add the energy, right? Number 3, so it was B for that one, right? Number 3, which labeled process is correctly paired with its direction? So in sublimation, does gas become a solid? No. It's the other way around, right? In deposition, does a solid become a liquid? No. In condensation, does a gas become a liquid? Yes. Condensation is when you have, like, for example, water vapor condensing on the side of a cool glass, or cold grass out in your yard, or your windshield. It let dew all over it. And then finally, we have melting. Is melting liquid to a gas? No. So C is the correct answer. For a sealed container, we've got a sealed container. That means no air or water in or out. Yes, Merriman? Sealed container. Okay. It has both water and water vapor at equilibrium, meaning there's no evaporation going on, there's no condensation going on. They're just neutral. If the temperature in that container increases, which will occur? Will more water vapor condense into liquid? Wouldn't it have to go colder? They're saying you're heating it up. Temperature increases, so A is no. The rate of evaporation decreases. I'll ask the question again. You got a sealed container, water and water vapor in there at equilibrium. If you add temperature, if you increase the temperature, will the rate of evaporation decrease? No, it would increase, wouldn't it? Would the vapor pressure decrease? No, it would increase, wouldn't it? As more evaporation takes place. Would more liquid evaporate into vapor? Yeah. 5, which of these best explains why ice requires energy to melt? A, energy breaks the bonds holding molecules in a rigid structure. Do we need to go back to the reading? Remember, it's that battle, right, between the molecular attraction versus the molecular motion. You guys are looking at me like I'm crazy. What's up? All right. Which of the best explains why ice require? It is that one. Does this make sense though? Like, energy makes molecules lose kinetic energy. That's just like nonsense statement. Energy causes a chemical reaction that creates water. No, we're talking about like phase changes. It's just physical change. Energy forces molecules to form stronger bonds. No, it weakens those bonds, right? Okay. And then getting more into your question, yours, okay? Explain how energy changes during evaporation and condensation. Give real life examples. Dew. You guys know what dew is? D-E-W. Yeah, the droplets on the grass in the morning. It's like soaking wet grass, but you like, I swear it didn't rain last night. Okay, so what's happening there is you've got moisture in the air, water vapor, humidity, and then it condenses onto that cool grass or the windshield or whatever it is. And then by mid-morning, usually what happens? It evaporates back off, okay? Number 2, this is for yours, or no, it's not either. Number 3 is yours, Merriman. Merriman, yours is number 3, okay? Number 2 says, describe how pressure affects the boiling point. Did I already ask you guys about the noodles or rice? How many of y'all do some cooking? Okay. Have you ever seen on a box of noodles or rice or something that you're going to boil where it'll actually say like, hey, at altitude, at a certain number of feet above sea level, what happens to the boiling point of water? It decreases. It takes less heat energy added to make water boil at altitude. Okay. Another thing that we talked about earlier was air conditioning systems, like in a car, for example. Sometimes the system will get fouled up, and whatever reason, if they need to replace a component, maybe the compressor goes bad, they'll have to pull the refrigerant out of the system. They do that by creating a vacuum. Does that make sense? So they basically suck all of that refrigerant out of the lines. Why do they do that, by the way? Why can't they just vent it? It's not good for the atmosphere, right? It's not good for the environment. So they capture it by creating a vacuum. The liquid that's in there boils off, not because they raise the temperature, but because they drop the pressure. Does that make sense? So if you drop pressure enough, things will evaporate. Okay, so that's a good example for that one. Compare and contrast sublimation and deposition, including, so we're gonna go back to the windshield or the grass. How many of you ever walked out in like when it's cold, the wintertime maybe, and the grass is kind of crunchy because it's frosted? It's frosty grass, or there's frost on your windshield, okay? Hello. That happens because the glass is below freezing, but the air is humid. So it goes straight from water vapor, deposition happens, and it creates that frost, that frozen water on the windshield. But you can tell the difference between frost and ice by the texture, right? You notice how frost is more rough. Now, if you had warmer temperatures, it would condense on the glass, okay, and then it could drop temperature and you'd have ice. There's a difference between ice and frost. You guys understand that? Yeah. Okay, so then the reverse of that is, has anybody ever seen somebody? Hopefully nobody in here, but you probably know somebody that'll clear a spot on the windshield of the frost, and then they're driving along looking like this through that one spot, or like they just using the defroster, and it starts really small, or it's cleared on the windshield, and then it grows, and as they're driving, right, it could even just be the dry air coming by. It doesn't evaporate, it goes straight from a solid frost, right, to a gas. That's sublimation. Make sense? It never melts. What's up?
Why is the boiling point less at higher
How would I explain that? That's a really good question for explanation. You got me. Let's Google it. I am not beyond using the Google machine sometimes. Why does the boiling point of water decrease at higher altitudes? Boiling point decreases as elevation increases. There's less air pressure. It's about pressure pushing down on the surface of the water, allowing water molecules to escape into the vapor phase with less heat energy. So it's about pressure, atmospheric pressure. Yes.
Is it like a drastic change, or is it like 1 degree?
The further the less pressure, the lower the temperature required. I'm sure there's probably a chart somewhere you could find that would show you exactly at what pressure the temperature required would be. Yes.
So does that mean the deeper you go into Earth, the more?
Yeah. So if you're at below sea level, you'd actually be at a higher, like more than 1 atmosphere pressure. So you would have to heat it higher. Yes. Another thing somebody said earlier is like, that's part of the reason why lid on or lid off right? Lid on, the pressure is higher than lid off. Does that make sense? Yeah, kind of neat. All right, moving on. Wait, was that it? I think that was it. All right, cool. Reading book?
I do.
Yeah.